Okay. All right. Are you ready? All right. So this is the last bit of spectroscopy, infrared spectroscopy. So this is the most fun. No, it's not. Well, what's that? Okay, I wish it was fun, or I wish it were. Okay, so, but we didn't finish? Okay, sorry, we're not. Wait a second. Pam's head is not in the right place today. I want to close out of it. Yeah. You're right. Okay, I don't think I'm gonna get to proximate analysis. Where is this? Okay.
We didn't know. I think we left off on slide 16.
Yeah. That's the last slide I know.
I had not put out the multiple choice question.
Thank you for reminding me. All right, I also have recap questions and everything for you. Let's see. All right. All right. What's Beer's law? I think I asked it last time, didn't I? Come on, you guys, you know it. Just say it in simple terms, not the equation. You don't have to, but if you know the equation, that's fine too. Thank you. Absorption is proportional to concentration, and its absorption equal ABC. A is absorptivity, B is the length that the light travels within the sample, and then C is the concentration. All right, and when is Beer's law applied? What's the characteristic of the light? Monochromatic, a singular wavelength or wavelengths very, very close to each other. Okay. Why absorbed light is not simply equal incident beam minus transmitted light. So if you remember, so you have your sample cuvette or tube, whatever. And then that's the incident beam or PO. And that's the transmitted light, the light exiting. Why isn't this minus this equals absorption? Yes. Reflection can happen. What else can happen?
There's a lot of scattering.
Light scattering, reflection. So not all the light really gets to the sample. Some of it doesn't. It gets reflected. Some of it, if you have particulate, gets scattered. So that's why we take the relationship and the log of transmittance. Negative log of transmittance is the absorption, and that's linearly related to concentration. How does a monochromator function? Yes, Razi.
So it splits the light to like the different wavelengths that you want them to analyze it.
Absolutely. So you take the light, all of the light goes into a diffracting system, and the diffracting system is diffracted into multiple individual wavelengths, and you select the wavelength. Usually, which wavelength you select? Remember, Tina? Lambda max, which is the the wavelength at which you have maximum absorbance. Most of the time, unless you have interference, you choose another one. Yeah, We answered the last one. Okay. A couple of other small things I want to talk about is instrumental error, also known as noise. So you would have absorbances happening, but at very, very low concentration, meaning not concentration, low signal. And so you usually correct for that when you run a blank that has the same components as the sample, and you try to correct for instrument error. Also, you try to correct for the noise to make sure you have absorbances higher than the noise. So you choose a concentration where your absorbance reading, usually I mentioned last time, between 0.2 and 0.8. So your absorbance is really higher than a noise. A noise could give you an absorbance of 0.01, 0.08, or something like that. Very, very low signals. So you really want to be away from that potential noise. So with that, what would be correct here? Yeah. All of them. So it has to be small relative to how samples are different from each other. So you have a sample that has an absorbance of 0.6. You have a sample that has an absorbance of 0.7. You want to really differentiate from that. So you want the noise not to be as big as 0.08, the noise to be small. And that happens when you correct for it, 0 transmission, 100% transmission, correct blank, and so on. So you do the best you can to reduce that error or noise. Okay, good. So in terms of an instrument, we kind of talked about this multiple times. You have a lamp, and depending if it is visible light or UV light, it will be either tungsten or deuterium. And the lamp gives you the light that goes into a monochromator. And that monochromator will cause a diffraction of light. So, and then you have multiple wavelengths and you allow specific wavelengths to exit and go to your sample. So a singular monochromator that goes to your detector. The detector can be a phototube detector or photomultiplier detector. So this is a phototube. You have one cathode and one anode, but often you want to multiply the signal so that you enhance sensitivity. So you use photomultiplier tubes, exact same one you have in your AA, the spectrophotometer that you used for atomic absorption. So here I mentioned it briefly with AA. So you have the light that reaches the detector, hits a cathode, an electron gets transmitted, it goes to a dynode and then multiplies. And it keeps multiplying until you have it multiplied quite a bit and enhance the signal and therefore enhance sensitivity. The photodiode array detector, you've used it in the HPLC lab where you got a spectra, you got a fingerprint. So all the light from your lamp is going to the sample. So your sample now is absorbing at a lot of different wavelengths within its allowable energy level. So at this point, when the light that is transmitted reaches an array of diodes, so that's why it's called photodiode array detector. So it reaches an array of diodes, a lot of diodes. And each diode will convert a singular wavelength into an electric signal that reaches your processors, the processor that will give you a readout. So then you will have an absorption graph just like that, like you've seen for when you did the caffeine lab. So you have the x-axis as wavelength, the absorbance as y-axis, and then this would be at a singular time point, like every 0.1 or 0.01 second, you get a readout like that. So three-dimensional data is what you can collect. Wavelength, absorption, and time. So this is usually used to differentiate. So it's a fingerprint unless two compounds have the same functional group that absorbs light. So you probably, you remember maybe from Nigel's explanation that two isoflavones, two different isoflavones, one has sugar, one doesn't have sugar. One has the aglycone, if you remember from the mass spec as well. One is the aglycone and one is the glucoside. It's the same family, so that aglycone absorbs the light in the same range. One has a glucose and one doesn't. One comes out first because it has a glucose unit, makes it polar in a reverse phase system, and one is not polar, doesn't have the sugar, comes out last. When we open the spectra, shows up to be the same, but they're two different compounds. Because does glucose absorb light? Does glucose absorb light? No. No, it's not a chromophore unless you do something to it. So when you have these two isoflavones, one with sugar and one without, they are absorbing the same way. You think they're the same compound, but they're not really. They elute at different time, and if you do MS, they have different molecular weight. So it has certain strength and power to give you that fingerprint, but sometimes you need advanced analytical technique to differentiate between compounds that have the same chromophore. Okay? You want me to repeat anything? We're good? Don't be shy. I know it's Friday and you really want to go home. Okay. So the instrument itself, it can be something we call single beam. So you don't have a reference cell. So here, there is reference cell and there's sample. So double beam is when you have the beam is split using mirrors. Part of it goes to the sample and part of it goes to the reference. And then they both reach the detector and automatically you get correction for the blank. The reference has your blank, has all the reagents but your sample. So your reading is corrected automatically. But some instruments have a single beam, only the sample cell. So you would just put the reagent, you zero, or you take the measurement, take it out, put the sample. So each has advantages and disadvantages. When you don't have the reference cell, you want to zero more often because there might be deviation. So you'll notice this when we use the spectrophotometer for carbohydrate analysis and other analyses in the lab. It's like if you don't have double beam, you want to put the reagent, zero, take it out, do a couple of readings, and then make sure you zero again. Because you get deviation over time and the noise increases over time. Okay, so basically, depending on what you have in the lab, each comes with advantages and disadvantages. If you have double beam, that means a beam that's split into two, you have reduced the radiant power because your light is splitting into two, so you lose some sensitivity. So I needed to check if the new edition has the same table. 7.2, it used to be in the older edition. I didn't check again. But basically what this table is showing you is that different components within a molecule can absorb light. Yes.
So for the double, you said the double meaning, and the loss of.
Yes, because the beam of light is split into two. One going to the reference and one going to the sample, so less light intensity is reaching. So you lose a little bit of sensitivity. And you adjust your concentration accordingly. Yeah, okay. So
Onion goes to, what thing goes to what, like?
going back, let's go back.
Yeah.
Oops, back. So this is the source of light. So the source of light hits a mirror or something that splits it. I think it's a mirror. Part of it goes to the sample cell and part of it splits into the reference cell. So the entire radiant power of the light gets split. And because of that, you have very less radiant power, you lose a little bit of sensitivity.
Yeah, thank you.
Of course. Okay. And here I'm just showing you that different compounds have different groups within them that absorb light at different wavelength. So you would see that they have lambda max, so there is maximum absorption at a particular wavelength, and their epsilon in molarity, per molar per centimeter. Remember, I want to write it again here. So when you write absorption as such, this means your distance is in centimeter and the concentration is in molarity. So here the unit is per centimeter molarity, or you can write it as such, -1. That's fine. When the concentration is molarity, you refer to it as epsilon or molar extinction. So each of them have specific, it's a constant based on the wavelength for a compound that has a chromophore. Okay, so you see, this is just to illustrate every compound that absorbs light will have particular components in it that absorbs light and that have a specific constant absorptivity or molar extinction at a particular selected wavelength, which is usually lambda max. Now, a fluorescence, that was an absorption spectrophotometer instrument. A fluorescence have a little bit different setup, because if you remember, the incident beam or the light that is absorbed as a particular wavelength. But what about the light that is emitted or the fluorescence? What wavelength would it have? The same, smaller, or longer? Shorter or longer? Do you remember? So the absorbed light is of a particular wavelength. But the emitted light, the fluorescence, does it have the same lambda, shorter lambda, or longer? Longer lambda. Why?
To have a solar spin.
Energy, less energy. Yes, because emitted light is always of a lower energy level than the absorbed light, because some of the energy is dissipated as heat. So then we have less energy to emit. Therefore, the lambda of the emitted light is of a longer wavelength. So because of that, we said that when you work with a spectrophotometer or a fluorescence spectrophotometer, you want to set it at two wavelengths, the absorbing wavelength and the emitting wavelength, if you're quantitative. So, and how do we do that within the instrument itself? So we have the source of light. It goes into the monochromator, the wavelength isolator, same as monochromator. you get your incident beam, which is a monochromatic light that hits the sample. Oh, you can't see what happens next. And then there is the transmitted light, which we don't want. We're not measuring absorption. So the emitted light is angled through mirrors to be perpendicular to another monochromator. Why? Because the compound, or there are molecules there that might be absorbing at the same light and emitting, absorbing the same wavelength and emitting other wavelength within your sample. You don't want that. You want a particular compound. So you select from that emitted light, you select the wavelength that has the highest fluorescence for your compound of interest. You want me to repeat this part? Okay. Yeah. So here, first of all, we select a wavelength using a monochromator, or wavelength isolated, means the same thing. That lambda max here, this assuming is the lambda max for your sample. And your sample is not a pure sample of one compound. You have multiple compounds. And these compounds might still absorb at that wavelength, but you're only interested in one of them. So they will all emit light, but and some may emit light, some will not emit light, some will emit light at different wavelengths. So we just want the one wavelength. Again, we want to keep it monochromatic. We'll select one wavelength that has the maximum fluorescence for the compound of interest. So that's why in this instrument, we have two isolators or monochromatic. Okay, and then it goes to the detector, and then we get the readout. Okay, we good? You have any questions? Yes.
Compounds that have both. And then like fluorescent.
You could. So then if you have compounds that might absorb light at the same absorption and emit light at the same wavelength, so wavelength for absorption is the same, wavelength for emission is the same for both of them, then you select a different wavelength that is not necessarily the maximum absorption or maximum emission happens to avoid that interference. So you just go, okay, lambda max is going to interfere with two compounds. So I'm just going to choose different allowable energy, but not as sensitive to avoid interference. Does that make sense to you? Yeah. Yes.
What if you have like two compound absorb same wavelength, but the other compound emits that?
Well, okay, now this is complicated. I didn't come across that. But again, you can always change the wavelength at which you do the absorption and the emission. You try to make sure you avoid interference as much as possible. It's not always perfect. And if you're not able to, you just use different methods. You just say, I give up that time. I'll just do something. You know, they're always hurdle. Yeah, your situation is not impossible. It can happen. That's why you can't always have one method of analysis. If this doesn't work, you go to another type of. Okay, we're good. Now we can go to infrared. Okay. Okay, so it might be a little bit crowded. Let me break it down for you. So infrared is right in this region. So this is the red visible light. So infra to the red and the wavelengths are longer in that region. So they carry less energy or more energy. I'm going to keep that ingrained in you. Huh? Less energy, less energy. Yes. Longer wavelength, less energy. So this region has less energy than the visible NUV region. That's the UV. This is the visible, and this is the infrared, longer wavelength, less energy. So infrared spectroscopy, we are in this region. I don't know why we can't see this. There is something down here. Why can't we see it? How can I get rid of this? Yeah, how do I do full screen? I am on full screen, I thought. Interesting. I don't know. But here what you can see is the range of the entire infrared, which is from 0.08 to 15 micrometers. That's the range that you can see here. And then you have the mid IR and then the near IR. The near IR is closer, meaning near to the red, so has higher energy and shorter wavelength. And then you have the mid IR somewhere in the middle here, where you have 2.5 to 15 longer wavelength than here. But it's still in the mid range. We don't care about far IR. Input analysis, near and mid IR is where we deal with. And then the way the interaction with light and the determination whether it's qualitative or quantitative is based on dispersive, where the light gets dispersed and you have a monochromator, or transmittance, measuring the transmitted light, or measuring reflectance of light, or using all the light that reaches the detector, reaches the sample and gets to the detector, and you get a spectra. And you use calculations called Fourier transform calculations, very complex. Usually you don't do it by hand. The system will do it for you and spits out the qualitative and quantitative data for you. All right. So the applications are really very similar to the UV vis spectroscopy. It's very similar. We do qualitative detection, identification by having a spectra that is unique or fingerprint. It's very important for structural elucidation because what happens here is you're measuring vibrational energy of functional groups. So you would have a molecule that has multiple functional groups, and you will be measuring vibrational energy at different wavelengths or wave numbers so that you get an idea of the entire molecule. We can do quantification. It's very commonly used as a rapid method of analysis, compositional analysis. And we'll talk about that. And we can use it as quality assurance. So quickly going through in a plant, a production plant, and you really want to monitor moisture level as you go through the process. So you take samples out, you run them on the IR, gives you within seconds or minutes, depending on the number of samples, gives you the results. You go and correct the processing if you need to. And forensics, we are suspecting a contaminant. This contaminant has a unique spectra in the IR region. We run our sample with and without that contaminant. So we have a standard, we run it, and then we run the sample that we're suspecting, and then we see a unique spectra. So that's kind of a forensic. So you would determine contamination. And I'll give you later an example for melanin. So The cool thing about infrared spectroscopy, it's non-invasive, meaning it does not destroy your sample. It's non-destructive. So you can run it through IR, your sample, and then take that sample and use it for something else. So that is very, very useful, especially when you have limited amount of sample. So that's what it means when it's non-invasive, non-destructive. So you just run it through IR, get a reading, and the sample remains as it is. It's very rapid. You get the results very quickly. And usually there's hardly any sample preparation. You just have, for example, sample to be milled. If you're doing, if you want to measure composition of a grain sample, you make sure you mill it and it's a homogeneous particle size. You put it in the sample compartment to a specific thickness, and that would be all that sample prep that you would need to do. It's suitable for routine analysis, quick quality check, fast, energy efficient, environmentally friendly. But the one thing that you need to note of, and I will ask about, it needs to be calibrated. How do we calibrate an IR instrument? What do we do? What do we feed it with? Can you, I think I mentioned it briefly in one of earlier lectures. How do you calibrate an IR? So the IR, you need to tell it, this sample, you will run standards and you say, this sample has 5% fat. This sample has 10% fat. This sample is 12, and so on. And then you do the calibration. How do you know what do you use to determine the sample fat? The question?
Yeah, yes.
Okay, so you want to calibrate the IR so that you have an unknown sample and you have standards. So your standards, let's say you want to measure fat content. So your standards have different levels of fat. 1.5, 1.10, 1.12, 1.50. Then you would say, okay, this is the concentration of the sample, you feed it, and then you run the calibration. You have a calibration field, you run your unknown, and it gives you the fat content of 7. But how do we determine the fat content of the sample that we gave it? Somebody had told us, right? But we just good. So you want to use an official method of analysis. And we will learn a lot of different official methods of analysis for measuring composition. For fat, you would do either Mojo, Modiner, or Soxlet, or you run Tarias composition and calculate that. So, and then you know these are the standards, and you input. Every time you run a standard, you input the concentration based on an official method of analysis. So I think it's as probably the first or second lecture, and I call them primary methods of analysis. Official methods of analysis are known also as primary methods of analysis. So this is bring us to the first or second lecture into analysis, to link things together. So this IR is a secondary method of analysis that has to be calibrated by a primary method of analysis. This is very important when you work out there in industry or in lab and you want to calibrate an IR, you really want to know, why am I doing this? Because this is a secondary method of analysis. It needs to be calibrated based on an official primary method of analysis.
You also take a background, right?
The background?
Yeah, like a background before you.
It's very, very rare that you have a background. There's background noise that you would calibrate the equipment itself with 0 transmittance and 100% transmittance. But your sample usually doesn't have any reagents, so there's no length that you would have to prepare, right? Usually the blank that we use to zero the instrument made up of the reagents you use to prepare your sample. But here you have, let's say, grain or milk. There's no reagent as is, you measure them as is. So you only try to calibrate for the instrument notes. Does that make sense to you, Joe? Or that next question, or you're asking something else?
Yes, but how can we get back to our technology?
The background, which is considered the instrument notes. So, yeah. So it's
Right,
you run an empty.
yeah,
For air, okay, it depends on the instrument, but for example, did you guys go do STIR? Did you? I'll have to check, but I don't think we run an empty anything. But depend on the instrument grade. Okay. So the concept is the same. You have source of radiation that gives you IR radiation. And then sample absorbs, and then light is transmitted, and then it goes to the detector, and you have a spectrum. Fingerprint, no two structures have the same fingerprint. Two structures, two functional groups that are different, like a carbonyl group and the OH group. Carbonyl group from a fatty acid, and then an OH group from lactose. They won't have the same finger or the same absorption. There might be slight overlap, but not the exact same. So in the IR region of the light spectrum, the energy levels coincide with vibrational energy level, allowable vibrational energy level. And every molecule has its own allowable vibration level. So what is vibrating? The bonds of atoms within the molecule. They are constantly vibrating, but when they absorb energy, they vibrate a little more. And when they go down from excited to ground state, they go back to their original vibration. So do we have vibrational energy when it's only atom, like what you did in AA? No, it's only electronic. In a molecule, what do you have? You have electronic, you have vibrational, you have rotation. But in the IR region, you don't have electronic energy. You have only vibrational energy. So the molecule cannot go from this level, 0 level electronic, to the first level or second level electronic when we're only giving it IR radiation. It's not enough, it's weak, it won't cause electronic change. It will cause vibrational change. Okay, that's what everything on this slide says. So this is the same as in the introduction. So energy equals a constant multiplied by the frequency. So same thing applies here. It's just, it's a different frequency, different wavelength, different energy levels. Oftentimes, when you are measuring IR, you get the value of, instead of saying wavelength, you count wave number. And this is the relationship between wave number and wavelength. So it's the inverse, wave number is inverse wavelength in centimeter. All right, so this is just showing you that the bonds within a molecule, they're in constant motion. I'm so upset that you can't see these. Why is it like that? I don't know. Was it always like that? It's just today?
Sometimes the taskbar goes away.
It's not going away now. Why? How can I hide it? Oh, how does the emitted light move 90 degrees through mirror and engineering construction of the spectrophotometer, which I'm not very engineering oriented, but they do design it that way. Okay, I thought he was gonna tell me how to remove this. A good thing I saw the question. All right, this is annoying. It's just giving you names of the type of stretching and bending. So the bonds can bend, they can stretch, and they get compressed. So basically they're in constant motion. All what I want you to know is they're always in constant motion. And when an IR energy is absorbed, the vibration increases. And then when it goes to ground state, goes back to their state, regular state of stretching and bending, which is constant. That's all what I want you to know here. Okay, hold on. Oh, where is there? What? Was there another? Where's that noise coming from? Okay, I don't know if something else is happening. So it's the same with absorption of UV and visible light. So the same thing here. If the energy projected is within the allowable energy levels for vibration, then the molecule will absorb the light. If it's not, it will ignore it, it won't absorb light if it's not within its allowable energy. So what this is saying is really the chemistry of it, because the bonds are bonds between electrons, and there's always this dipole moment happening. So when the molecule absorbs IR, it changes the distribution of the electron, more on one side, more with one atom and less with another atom. That's kind of what it is. What it means is the electrons move differently, influencing the bond vibration. But don't worry too much about it. It's just I'm explaining what you're reading. But I won't ask you this question. All right. This is a typical mid-IR spectra. In mid-IR, your peaks are really sharp and defined. You'll see later with near IR, fun time goes by so fast, right? Or is it just me having fun? Okay. Well, let me finish this, then we'll finish on Monday. But before I lose you completely, I just want to say that these peaks are really sharp and defined. In near IR, they're more of overtone, big overlapping peaks. So when you use mid IR, this is all these peaks are coming from one molecule, one compound. So this one compound have different functional groups. You have a double bond here, you have what do you call that? Hydrocarbon bond. So you have different bonds. So here's you have a stretch of the carbonyl, you have another stretch here. So every peak here is for a different component within this entire molecule. So you don't have multiple molecules. These are functional groups within that one molecule. So that's the fingerprint of butyl aldehyde. So this is what's cool about it, because it gives you an identification power, and also you can quantitate. And it is usually unique for the compound. So it's very, very powerful. And this is an example of in an alkane or alkene alcohol, amines, and so on. It tells you what are the compounds that absorb IR radiation and change in vibration energy and at what frequency or wave number. Okay, so of course you want to memorize these. No, nobody's taking me seriously at this point. Before you leave, can you answer this question? Sophie? All right. IR radiation, what kind of energy is associated with IR radiation? Vibration, electronic, or rotation? What is it? You tell me.
What?
Is it electronic? Vibration? Vibration. Does the atom vibrate on its own? No. You got it. Okay. So it doesn't. It doesn't. So we cannot use IR for atomic absorption. Not chromatography, spectroscopy. All right, so false, because it's an atom, not a molecule. All right, I was hoping to get into the moisture. What am I thinking? We never got there. Not even halfway in this. Okay, never mind. Have a wonderful weekend. All righty. Yeah. Huh?
Hand out tests on Monday.
Yes, but I forgot the folder in my office. If you want to walk with me, or do you have
Ham
class?
class right after.
Do you want to come? No, where are you going?
I'm going to work right after that, so
Oh, okay.
Friday.
So I'll bring it with me on Monday, or maybe you want to shoot me an email so that I
Okay.
remember. It's in my office.
I just
Did you see your grade?
No, they're not posted. They're hidden still.
Hello. Can you tell? No. Okay. I told Charlie to post it.
It might. I know. I sometimes stuff gets hidden and.
Can you please let Charlie know that the grades for the quiz are hidden between on Canvas?
Yeah,
Just to
yeah,
unhide them. I thought she entered them.
Yeah. Okay. I'll check it.
Yeah, but I know what you got. You wanna know? Huh?
Sure.
Do you wanna know that your grade is the highest in the class? You got the top. Hey, you got 29 out of 30. Was it? You had no, I remember because you did very, very well. Oh, you're making me cry now. I'm very easy to cry. Yeah, so you did really well. Yeah. I'll bring it to you on Monday, but you should be able to see the key at least.
So what I did, like,
It's on. It's been 2 weeks probably. It's been 2 weeks.
25.
How are you feeling?
Sorry, like that. I need to take. When I saw like, well,
Did you lose the smell? No, oh, yeah, it's bad feeling. I know how it feels.
yeah. Kind of a week.
Yeah,
I really
yeah. But at least this will make you happy for the weekend. And then Monday, are you Monday lab or Wednesday? Wednesday lab. Just remind me for sometime during.
Message me too. I mean, you probably haven't seen it, but
No.
I work somewhat normal.
Oh, let me see. Did I stop recording? Oh, shoot. Did I not stop recording? I didn't stop recording.